K2-18b. No, it's not a character from Star Wars. It's a planet 2.5 times the size of Earth and 700 trillion miles away, and it could be home to living organisms.
Here's what we know right now, Pamela. The James Webb Space Telescope is so powerful that it actually can analyze the chemical composition of atmospheres from far, far away.
April of 2025. Something odd in the data is shown by a little drop in the brightness of a faint red star. A possible biosignature from a world over 100 light-years away has been reported by astronomers. Dimethyl sulfide spectral fingerprint in the exoplanet K2-18b's atmosphere. DMS is a gas that is nearly solely created by living things on Earth. Furthermore, if verified, this finding would be the most compelling indication of extrasolar biological activity to date. The news garnered international attention. Has the chemical aroma of life on a far-off planet been picked up by the James Webb Space Telescope? A new phase in the hunt for life begins amid the quiet of space. However, we must comprehend the stage on which this drama is playing out before we can make any judgments. The actual planet K2-18b. What sort of planet could contain a signal this alluring? The discovery and characteristics of this fascinating exoplanet mark the start of our adventure. A far-off exoplanet called K2-18b circles the cold red dwarf star K2-18. Situated in the constellation of Leo, approximately 124 light-years away from Earth. During its K2 mission, NASA's Kepler Space Telescope made the initial discovery of this alien world in 2015, when astronomers observed that the planet periodically transited its star, resulting in minute dips in starlight. They infer the planet's fundamental characteristics from those dips. Its mass is approximately 8.6 Earth masses, and its radius is around 2.6 times that of Earth. It falls under the sub-Neptune or mini-Neptune group as a result. Smaller than the icy giants Neptune and Uranus, but larger than Earth. The planet orbits within its star's habitable zone, which is the area where temperatures may permit the existence of liquid water despite its size. Despite having a relatively short year, approximately 33 days, K2-18b receives almost the same amount of light from its red sun as Earth does from ours because of its close orbit around a faint star. Depending on the greenhouse effect, its estimated average temperature is around 265 Kelvin or 17 degrees Fahrenheit and might be Earth-like. Notably, K2-18b was notable from the start because of its composition and location. Water vapor was discovered in the planet's atmosphere in 2019 by scientists using the Hubble Space Telescope. Water vapor was observed on a tiny exoplanet in the habitable zone for the first time, a finding that sparked global enthusiasm. It proved that the planet may have a sizable atmosphere with water, which is essential for life. With this finding, K2-18b became a good target for more observations. Is it anything more exotic or just a larger replica of Earth? Before long, every piece of data suggested a completely new class of worlds. Therefore, K2-18b does not quite fall into the typical classifications of gas giants or rocky Earth-like planets. Rather, astronomers believe it may be a member of the Haitian planets, a recently suggested class of exoplanets. Haitian is a portmanteau of ocean and hydrogen, created in 2021 by a group at Cambridge University to characterize planets with seas and atmospheres rich in hydrogen. These planets are bigger and heavier than Earth. They might be up to 10 times as massive and possibly 2.6 times as radial. It may still provide mild surface conditions, though. K2-18b nearly fully matches this profile. It has been referred to be the top Haitian contender. How might a Haitian planet look? A globe with an ocean hundreds of miles deep and an atmosphere dominated by hydrogen and perhaps helium as depicted in the idea. That kind of atmosphere may go farther into space because it is lighter and less thick than the nitrogen-oxygen mixture found on Earth. Ocean heat may be retained by a thick layer of hydrogen that serves as an insulating layer. Numerous stars might be orbited by Haitian planets. This size of sub-Neptune is thought to be rather frequent in our galaxy by astronomers. However, these medium-sized planets were not the subject of research for a very long period. Now, that is changing. Astronomers are reconsidering the limits of habitability in light of the possibilities of such worlds. As stated by Nico Madhuston, the principal author of the article reporting the finding and an astronomer at the University of Cambridge, these results highlight how crucial it is to take into account a variety of livable situations. The bigger Haitian worlds are far better suited for atmospheric investigations, but historically, the hunt for life on exoplanets has concentrated on smaller rocky planets. In other words, because their rich atmospheres are simpler to probe over light years, these planets may present the highest possibilities for finding indications of life, even if they may resemble several Neptunes more than Earth. The concept of Haitian planets has allowed our imagination to explore new avenues. However, we need to examine K2-18b's atmosphere and structure as thoroughly as the data permits if we are to fully comprehend its nature. The planet's size and density allow us to deduce its interior structure. K2-18b has a density of around 0.1 pounds per cubic inch, making it neither a gas giant nor a pure rock. According to the best models, this is a multi-layered universe. It most likely has a rocky core composed of metals and silicates in its core. Above it, a layer of high-pressure ice develops as pressure pushes water into strange shapes, and under the correct circumstances, there may be a huge ocean of liquid water atop this solid layer. A thick atmosphere full of hydrogen and maybe helium surrounds everything. In essence, K2-18b may be a landless ocean world with global oceans beneath a sky dominated by dense hydrogen. The thickness of the hydrogen atmosphere determines whether or not this planet has a liquid ocean. And very thick atmosphere might cause the water underneath it to experience crushing pressure and heat, perhaps creating a supercritical fluid, an environment that is probably inhospitable to life rather than a real liquid or gas. However, the water layer may preserve more Earth-like circumstances that are conducive to life if the hydrogen layer is relatively minor. The topic was covered in the early phases of the study. Without a clear ocean surface, early estimations indicated that water on K2-18b may exist in a heated supercritical condition. Later research, particularly with the use of fresh JWST data, suggested that the atmosphere might not be too thick. Indications of a genuine ocean-atmosphere interface are present. Stated differently, there is a real ocean of liquid water underneath the gas. The lack of ammonia is one of them indicators. In an environment that is rich in hydrogen, ammonia should be present unless it has a place to go. Given that ammonia dissolves readily in water, a liquid ocean would be the ideal sink for it. The idea that there may be a water ocean beneath the hydrogen-rich atmosphere is supported by JWST's detection of methane and CO2 in the air of K2-18b, but not much ammonia. If there is an ocean, it may be far deeper than any on Earth, and depending on warmth from the atmosphere and planet's interior, might even be heated. Where the colder layers of space meet the wet, hydrogen-rich air, the ocean may be obscured by dense clouds. As we previously discussed, the water would ultimately turn to ice under this ocean due to pressure, perhaps obstructing direct contact between the water and the rocky core. Life is affected by this. The ice cover may prevent mineral movement at the ocean floor, which might limit nutrients and make it difficult for any biological activity to occur. However, life on such a world may function similarly to Earth's deep-sea extra life, obtaining its energy from chemical gradients or dimly filtered celestial light. But for the time being, these theories are only conjecture. The James Webb Space Telescope, which was able to sniff the air of K2-18b and ascertain its composition, is the main source of what we do know. And we'll concentrate on it next. Scientists use JWST, which is excellent at infrared spectroscopy and can identify these chemical fingerprints in distant atmospheres to reveal the atmospheric secrets of this far-off globe. JWST used a near-infrared spectrograph, slitless spectrograph, and near-infrared imager to examine K2-18b when it crossed in front of its star in 2023. This is how it operates. A very little amount of starlight enters the planet's atmosphere during each of K2-18b's 32.9-day transits of its star. Certain light wavelengths are absorbed by molecules in that environment, resulting in dark lines or other patterns in the spectrum. The sight can determine the chemical components of the air by dividing the starlight into a rainbow and examining the portions that are absent. It is comparable to deciphering the molecular barcode of the planet. The transit spectroscopy technique, which has a far better sensitivity and a wider range of wavelengths, is now used by JWST, which was initially used by Hubble to hint at water vapor on K2-18b. This satellite telescope's observations were excellent. There were obvious indications of carbon-bearing compounds in the atmosphere's infrared spectrum. In particular, James Webb identified carbon dioxide and methane in the atmosphere with certainty. The first conclusive proof of atmospheric composition on a sub-Neptune situated in the habitable zone was provided by these results, which were revealed near the end of 2023. A hydrogen-rich atmosphere is indicated by the presence of methane and CO2 in various wavelength bands. It is also anticipated that water vapor will be present. However, spectral features indicate that if it is likely in trace amounts in the upper atmosphere or perhaps as high-altitude clouds. Notably, as was already indicated, there was very little ammonia, which strengthens the argument when paired with methane and CO2. It's possible that K2-18b is a high-ocean world with an ocean. Underneath, a transmission spectrum map of the planet's atmosphere that illustrates the amount of starlight absorbed at various wavelengths has been produced by scientists. The model that most closely matches the JWST data is shown by the blue line. The presence of methane is indicated by prominent absorption properties. These molecule fingerprints are highlighted by the purple, red, and green patches. An interesting section at around 3.3 microns suggests the existence of dimethyl sulfide, or DMS. What does this signify? Let's dissect it. Scientists discovered a specific characteristic in this spectrum, an absorption spike that, save from one, didn't correspond to any chemical that should be present in typical subnoon atmospheres. The results from their atmospheric models suggested that dimethyl sulfide gas was present at specific wavelengths. With a low level of confidence, the team reported this as a potential DMS detection. We'll talk about the warning soon. Nevertheless, given how intimately DMS is related to life processes on Earth, it was sufficient to generate further investigation. As a result, K2-18b was shown by JWST's data, which included wavelengths ranging from around 1 to 5 microns, as a hydrogen-rich world with methane, CO2, and perhaps even a chemical that is linked to life on Earth. This was a significant event as it was the first time a combination of this kind was found on a planet within a star's habitable zone. This is what we have then. An atmosphere that would be compatible with a possibly habitable ocean-bearing planet was discovered by JWST. There is a lot of carbon dioxide and methane. There is a shortage of ammonia. Moreover, a surprising trace of dimethyl sulfide is seen. These clues imply that biological activity may be influencing the atmosphere and that it may be in communication with the ocean. However, how credible is this telling of the tale? The next stage is to comprehend why DMS is so important and why researchers are treating this finding cautiously. Dimethyl sulfide's significance on Earth is the reason it created such a stir. It is well known that life on our planet produces nearly all of the DMs. It is a sharp gas that contains sulfur and is frequently connected to the faint scent of cabbage, the sea, or an ocean breeze that is evident close to blooming plankton. Microscopic marine plankton, especially certain bacteria and phytoplankton species, produce a substance called DMSP in the oceans of Earth, which they use to control their cells. DMSP decomposes and releases the gas DMS when these organisms die or eat. Consequently, marine phytoplankton provides the majority of the DMS in Earth's atmosphere. Almost no substantial abiotic non-biological sources release this gas in significant amounts into the atmosphere. Hydrothermal vents in volcanoes, for instance, release a variety of sulfur compounds, but not much dimethyl sulfide. As a result, finding DMS on Earth is equivalent to finding evidence of life. DMS has been suggested as a possible biosignature gas for exoplanets because of this. It's like discovering smoke from a campfire in the middle of a forest. Since fires rarely start on their own, you would know someone is there right away. Furthermore, this gas's duration in the atmosphere is brief. The molecule decomposes in the presence of sunlight on Earth, usually within a few days to a few years. This means a continuous active source is needed to maintain a noticeable concentration of DMs. It suggests that something on the planet is consistently releasing the gas, if K2-18b does really contain this molecule in measurable proportions. Astrobiologists believe that something may be biology, an extraterrestrial biosphere in a fictitious ocean. It's also crucial to remember that methane, which is also present on K2-18b, is frequently seen as a biosignature in and of itself when it is discovered with CO2. Because bacteria on Earth are capable of producing methane in the absence of significant carbon monoxide levels, methane may also be formed abiotically in the case of an exoplanet, for example, during the planet's early development or during hydrothermal processes. Therefore, by itself, it isn't a smoking gun. But it's interesting when methane and carbon dioxide are combined without ammonia. Methane tends to decompose via photochemistry, unless there is a strong replenishing supply, which life can provide, according to some experts, making this combination difficult to maintain without biological sources. When you combine it with the preliminary discovery of DMS, you have a strong case for the possibility that a biological factor is involved, but exceptional proof is needed to support extraordinary assertions. Scientists are considering the possibility of a hint of dimethyl sulfide with a fair grain of caution because it is still far from proven. Let's examine why prudence is necessary and why other theories and difficulties need to be taken into account. The fact that the Dimethyl sulfide Verkobius is though necessary and the data is still inconclusive tempers the excitement around the potential detection of DMS. The signal from the JWST data has modest statistical significance, around 3 sigma, meaning that there is a 0.3% possibility that it is simply noise, according to the researchers themselves. 3 sigma is regarded as tentative in the scientific community, whereas 5 sigma, or around 0.000000003% possibility of coincidence, is usually the gold standard for discoveries. Other astronomers noted that the team is truly pushing the boundaries of what JWST can do with this detection in an explanation note that was included with the Nature News article about this discovery. The data from exoplanet observations is rather complicated. We are trying to find minute absorption characteristics hidden within a very weak signals noise. The light of a star traveling around a far-off planet through a narrow ring of atmosphere. Star activity, data processing techniques, and instrumental noise can all leave their mark on the signals in ways that either obfuscate or resemble actual chemical signals. Indeed, a different group's independent reanalysis of the 2023 JWST dataset revealed no discernible evidence of DMS or any other biosignature gases, indicating that the first indication may have been a statistical artifact. These experts caution that what one team perceives as a spectrum characteristic may actually be random noise fluctuations and characterize the spectrum as being highly noisy. Another crucial finding is that the JWST data suggests the existence of either DMs or DMDs, a similar chemical. In certain wavelength ranges, DMDS shares a similar spectral fingerprint with DMS and can be created by chemical processes in an environment that contains DMS. Dimethyl sulfide, for instance, can bind or oxidize to create DMDS. Consequently, a mixture of these sulfur-containing molecules may constitute the detection. The biological explanation could change a little if it's DMDS. Life on Earth can also manufacture this chemical, as evidenced by the emissions of some microorganisms and plants. Abiotically, However, it can also emerge through photochemistry with other sulfur molecules. There is currently insufficient evidence to make a definitive distinction. The possibility that dimethyl sulfide may exist on an exoplanet is perhaps the most significant reason to take into account abiotic theories. Modeling and laboratory tests have demonstrated that specific chemical reactions can produce DMS abiotically. For instance, scientists have shown that organic compounds may create tiny organosulfur molecules when subjected to high-energy radiation, environments similar to a primitive atmosphere, or cometary circumstances. The European Space Agency's Rosetta probe had been pursuing the comet 67P Churyumov-Gerasimu for 2 years, when a team from the University of Bern and Switzerland detected DMS and TACOM in 2024. The team took direct samples from the dust and gas cloud that the ice rock ejected. Comets are frozen, dead corpses. Nevertheless, one of its chemical emissions was found to be dimethyl sulfide. This demonstrates that the chemical is not solely biological. It's also important to recognize how intricate stellar activity is. K2-18b's host star is an active red dwarf that often flares in spots. Ultraviolet light from stellar flares might change the chemistry of the atmosphere, perhaps rapidly dissolving compounds like DMS or methane or, on the other hand, producing misleading signs of other chemicals. Anomalies in transit spectrometry can be caused by star spots, which are colder and darker areas on a star's surface. False detections may result if the planet passes over a spotted area of the star, because the starlight spectra may alter in a manner that is entirely unrelated to the planet's atmosphere. James Webb data analysis attempts to take these factors into consideration. However, it's not that simple. The finding is still speculative until we have further transit observations and, preferably, corroboration from completely other devices or telescopes. Whether this whisper develops into a distinct indication of life or disappears as an interesting aberration will be determined by the studies conducted over the following few years. Meanwhile, given the star has a big impact on the planet's habitability and how we interpret data about it, it is essential to understand the star K2-18 itself, including its flare frequency, spectrum, and age. In order to validate the makeup of the atmosphere, scientists are currently sorting through data and organizing additional observations. They are also anticipating the development of the next generation of telescopes, which will enable us to conduct more in-depth research on this world and others similar to it. Possibly more potent observatories are planned over the ensuing decades, which might corroborate this first result or possibly uncover completely new biosignatures. Scientists are specifically working on projects like the HABEX and the LUVOIS, two hypothetical flagship space telescopes that NASA has suggested for use after 2035. The capabilities of these next telescopes will even surpass those of the JWST. LUVOIS, for instance, imagines a telescope with a main mirror up to 16 yards across. In contrast, the James Webb has 7 yards at the moment. LUVOIS will be able to directly photograph the exoplanets and get incredibly precise spectra because to its large light collection area and sophisticated sensors. HABEX is a specialist planet search observatory with a star shade that is similarly built. Tens of thousands of kilometers ahead of the telescope, a huge occulting screen will fly in formation to block out starlight, allowing for the faint illumination of surrounding planets to be observed. The objective of both ideas is the same: to locate and investigate possibly habitable planets the size of Earth around sunlight and smaller stars, as well as to look for evidence of life in their atmospheres. What may these telescopes accomplish for worlds like K2-18b? First, they may use a mirror that is several times bigger than JWST to do more sensitive transit spectroscopy. A telescope of the LUVOIS type may collect a lot more photons from each planetary transit, thus increasing the spectrum signal-to-noise ratio. LUVOIS might definitively prove the existence of DMS, or rule it out if JWST pushes us to the detection threshold. Additionally, a mission might cover a wider spectrum of wavelengths that JWST is unable to reach, such as the ultraviolet and deeper infrared. This would make it possible to find more possible biosignatures or atmospheric markers. For instance, LUVOIs might identify organic haze or other molecules at shorter wavelengths, or look for materials like ozone in the UV. Crucially, future telescopes won't only be able to see transits, they might be able to image certain exoplanets directly. Since K2-18b is now orbiting so near to a faint star, direct imaging is difficult. Even with a 16-yard mirror, it might not be able to differentiate its light from the stars. On the other hand, heat emission might be directly observed. The planet's dayside light might be picked up by a powerful infrared telescope when it moves behind its star, providing an additional method for mapping temperatures and measuring air composition. Other missions will contribute in addition to LUVOIs and HABEX, though it will operate at shorter wavelengths and with less sensitivity than the James Webb. ESA's airborne mission, which is slated to launch in 2029, will investigate the atmospheres of hundreds of exoplanets, including potential candidates like K2-18b. However, Ariel will be able to identify any variations and improve measurements of known gases on K2-18b. All things considered, the next generation of telescopes, both on Earth and in space, will offer more vision and finer focus. Importantly, K2-18b will not be seen in a vacuum by these expeditions. They will investigate a large number of exoplanets with comparable sizes and temperatures. The notion that something general, maybe biological, is taking place would be reinforced if DMS, for example, were discovered on many Hyas-like worlds. It may indicate that K2-18b is unique if the chemical is found here and nowhere else, or it may indicate that the first discovery was only an anomaly. Either way, this world has established itself as a standard for research on exoplanets in the future. This story marks a watershed in our quest for alien life. Finding the next Earth, a duplicate of our planet with the same size, orbit, and star type, was the catchphrase for decades. Earth and K2-18b are not the same in the conventional sense. It circles a radically different sort of star, is considerably bigger, and probably has no land. By doing this, it has increased the number of planets that astrobiologists believe have promise. Basically, the biggest contribution this far-off world has made thus far is broadening our understanding of the universe's life. It has demonstrated that we cannot limit our search to one dimension. From rocky planets orbiting sun-like stars to several Neptunes orbiting red dwarfs, from biosignatures like oxygen and ozone to more unusual compounds, we must cast a broad net. Imagine an interstellar probe, outfitted with sophisticated artificial intelligence and instrumentation, setting off from Earth on a protracted voyage to this far-off world in a century or more. Our telescope suspicions are confirmed when the probe's cameras record a blue orb, illuminated by a dim star's reddish glare as it approaches the K2-18 system. It depicts a planet covered in dense clouds, with a huge ocean underneath. Upon arrival, the probe may parachute across a sky-tinted peach by the light of the red stars, filtered through a hydrogen haze, descending through the thick atmosphere. It directly samples the composition of the clouds as it moves through their levels. The capsule may be, if battered by fierce winds far stronger than Earth's, but ultimately it reaches a huge black and infinite alien ocean that stretches beyond the horizon in all directions. A copper glimmer is thrown over the wave crest as the local star, which is half the size of our sun, looms softly above. We are not alone, as the robotic investigator discovers a bacterium from this strange ocean as it descends into the sea. Such a quest, however, is much beyond our existing capacity. With the propulsion capabilities of today, 124 light-years is an incredibly large distance. For the time being, we continue to study from a distance, deciphering weak spectra and honing our hypotheses. Spectrum by spectrum, transit by transit, we are getting closer to comprehending this reality, and our watchful telescopes will keep listening to its murmur until we can send a far probe, so that even from a far-off ocean world, we will be able to hear life when it speaks.